এটা সুইচটা অন করো।
So, a very good afternoon to all present. It is a pleasure. It's a pleasure to be here today among all of you gathered together. So, I am very honored that Madam Principal would be here, and all the professors, all the students, and everybody who is gathered today for the sake of science. So, as Professor Kolkata said, that this is part of the social responsibility of all of us as science students to make others aware of our work. There are the essence of interdisciplinary work that we are doing at various parts of the country, so that you, the younger generation, can come forward, take this opportunity that the country is giving all of us to come into basic sciences, do more research into various areas of basic sciences, so that the country can progress. And this is to emphasize that how much natural sciences contribute to the country's progress and development. So all of you, I am guessing quite a big chunk of you actually have taken up basic sciences, physics, chemistry. And please remember that you are the future of the country, and you will be researching and progressing this country to be at par with international technologies, new inventions that will take us forward. So with that, I am very pleased to be here today on the occasion of the 75th anniversary of Gandhi Raj College. I am very honored to be part of this vibrant campus today, standing here, and I will be speaking on an equally vibrant topic, as you can see already from this small snippet. I will be speaking of light, how it moves around exotic objects called black holes. Now, black holes, there has been a lot of buzz recently about black holes. Every other week, we are seeing black holes popping up on the internet, on the newspapers. At least we all heard of the term black hole, and people are very curious what black holes are. We don't have any problem with the term black, but what we have problem is with the term hole. So, is there really a hole in the sky? And if it is black, how do I see it? So today we are speaking how to actually not only see black holes, but also how to take pictures of black holes. So with that, I start. So this is the basic outline of my talk. So to understand really what black holes are, which are very different from all the other objects that are there in our universe, for example, stars, planets, galaxies, and the universe itself. When we speak of looking at the universe, when we speak of seeing the universe, what we imagine are bright dots, say stars, or if you have a telescope, you can zoom into moons and even a part of the stellar constellations. But the main point is that all of them are bright. There is light coming from all of those, and those are reaching your eyes and the telescopes and the cameras and whatever, and that is how you actually see them. So it is very important to know how light moves and how light actually comes from those celestial objects towards us to really understand. That is the first step, and the second step would be then to image these lights, to capture these lights, and recreate what is there, deep inside the universe, to recreate their images. Now, black holes, as I said, are not your typical bright stars. Black holes are black because there is no light coming from them. So how do we see something which are black? So that there is no light coming. For that, we have to understand, come out of the classical physics that we have been studying up till now to your standards, say in your high school or your bachelor's degree. And we have to develop some new concepts. So today I'll be speaking of two very important concepts. One, light, and two, gravity. And I will be breaking your concepts, what you have learned up to today. First, gravity is not a force. And second, light does not always travel in a straight line. So how do I go about explaining it? If I tell you today that whatever you have learned up till now is not entirely true, then you will say, well, prove it to us, or you will say that we do not believe you until we see the evidence. So that is exactly what happened with Einstein. Both of these concepts were revolutionized by Einstein in 1915. Basically, he started working in 1905 with his special theory of relativity, where he said that the speed of light is the only constant thing in the universe. Neither distances are constant nor time is constant. Time can vary for you and me. What you measure in your clock can vary from what I measure in my clock if I am accelerated with respect to you. So I'll start with the definition of black holes. Then I will go and explain what they are and how they are formed. So black holes are very massive objects, like I said, stars. But stars, for example, our sun is a star, but black holes often start with a mass of greater than 1 solar mass. So that is somewhere around 5 sun masses, 8 sun masses, 10 sun masses, billions of suns concentrated, all those mass concentrated at a single point in space. Now that will seem to be very a mad concept, how can that be? So for that we have to understand that every object in the universe according to Newton, they exert a gravitational pull on any other massive object in the universe through his inverse square law of gravitational attraction. So gravity is basically a force according to Newton, which acts between two bodies, and the necessity is that both the bodies must be massive, they must have mass. So these black holes, they have such huge gravity. I will not call a gravitational force because I told you that gravity is not a force. They have such strong gravity that any particle, any mass, or any non-massive particle, for example, photons, light, cannot escape the gravitational pull of these massive objects. Because you can imagine that there are 1 billion solar suns concentrated into this object, sitting at the center of each of our galaxy. For us, for the Milky Way, is the Sagittarius A star, which is some 5 million solar mass. And this is how the black hole will look like if you look towards it through your telescopes. There will be a very dark region from where there will be no light coming, and it will be surrounded by very bright region from where obviously light will be coming, but in a very weird fashion. You will see a ring which we call the photon ring. I will explain what all of those mean. But this is a structure, what you will see is in your sky. So these black holes, please note that I have highlighted that light cannot escape from this black hole sitting at the center, and that is how you actually image a black hole. Imagine a body which is casting a shadow. There is a source of light, and then suppose this is my body, and I have a screen placed over here. So this object, if it does not glow, then there is another way to see this object is through its shadow. The part of the light that this is blocking would be your actual shadow on the plane, and from that shadow you will make out what this object's shape is. So that is what happens with black holes, but the twist over here is that it does not block the light. it engulfs the light, it eats up the light. The light falls into the black holes and that can never come out of the black hole. So black holes are characterized by an imaginary boundary surface. You can see over here, this surface over here, which is called the event horizon. And any object, massive or non-massive, for example light, once it passes inside, falls inside this event horizon, it can never turn and return back. So we have to understand really how light, what motion light is taking in these exotic objects. Because for normal objects, we know that light travels in straight lines, and if you have lenses, maybe the light can take separate bended trajectories, but light always travels in straight line. That is what we are hardwired to understand. Whenever we see any object, our brain takes it for granted that the light from that object is coming in a straight line. That is how, even if an object is not where it is, the brain will always pick up the light that is coming from it, and it will draw a straight line, and it will pick up the position from where the light is coming to be in that straight line. It will not be able to recognize any bending of light. But what happens if light actually bends around some object? What will happen? There will be a difference between the actual position that your brain sees and the actual location of that light which is coming from that object. So, I have to explain to you how light cannot escape, and for that, let us see how objects actually escape the gravitational fields of another massive body. For example, the Earth. Say this is my Earth, and classical Newtonian physics says that if you throw, say, another massive object, a ball, with some initial velocity, if that initial velocity is very low, the ball will go up and it will fall down. Now you increase the velocity. The ball will travel a higher distance, but then still it will fall down. But then you will always throw the ball with higher and higher and higher velocities until the time it escapes the gravitational force. What happens if it escapes this gravitational force is that the total energy of the ball, the potential plus the kinetic energy, it will cancel out. It will be zero, and the particle will be an unbounded trajectory, so it will escape. So if we solve this equation, it's a very simple equation. I have tried to keep the equations very low and give you a more intuitive idea. So this escape velocity is, it does not depend on the mass of the ball that you are throwing. It just depends on the mass of your gravitational body, the Earth. So this escape velocity for Earth, it is 11 km, for Sun it is 600 km. So you can get an idea that when the mass of this body is very large, as it increases, it is very difficult to say launch a rocket so that the rocket escapes from the gravity and it goes actually to a space orbit. But there is another way in which this escape velocity can increase and become very large. When the mass remains fixed, but the radius of the body, say, decreases. What happens? If we take the mass of the Earth and suppose we squeeze it, we keep on squeezing, this escape velocity will keep on increasing. So the question is, what happens if the R becomes very small? And this escape velocity, it increases and reaches the escape to the speed of light. What happens then? Then, if that happens, then instead of a ball, if I throw light, then the light particle cannot escape anymore. Because the speed of light cannot be exceeded, and you will have to exceed the speed of light to actually escape the gravitational pull of such a massive object. So for Earth, so this is actually, if I calculate R, if I put C over here and calculate R, so this is the radius of the massive gravitating body that will be required for such a phenomena when light cannot escape its gravity. So can you already feel that this is what the black hole is actually doing somewhat? But this is from classical Newtonian physics, and from here if we calculate, if we put the mass of the Earth, mass of the Sun, we will see that the Sun's mass, if it is compressed to 3 kilometers, within 3 kilometers, then if we shine a light from our torches from the Sun, the light will never reach us and the Sun will appear to be dark. So almost like a black hole already. And for the Earth, this is 9 millimeter. All the Earth you compress and you compress it to lower than 9 millimeter in radius, which I cannot even show with my fingers. Then if you shine a light, then the Earth will also not radiate any light, and Earth will also look black to an external observer in space. So far so good, but the issue is that this is from classical Newtonian mechanics. Now if you see over here, the calculation needs the mass of the body which you are throwing, right? But this mass is zero for light. Light has no mass. But what Newton is thinking is that light follows the corpuscular theory of light at that time, which says that light are not photons, they are particles, they are corpuscles, but they are very minimal mass. So Newtonian gravity then says that okay, if you put the mass, that small mass of light over here, and we calculate, then we can find out the event horizon radius, and that way we can explain if the light cannot escape in some situations. But the problem is that light, photon, as we know, is massless. So this gravity, Newtonian gravity, will not work on a massless body because Newtonian force is a force between two masses. So I must say that this was John Michell in 1783 who comes up. He's a geologist. He knows nothing about physics, but he's just thinking on your simple class 11th physics you could have also got at that time. And he comes up with this very simple explanation of he is imagining if there could be some stars which do not radiate, which we cannot see, which he calls dark stars. But the issue, as I said, he was working with Newtonian physics. And in Newtonian physics, light is considered to be a corpuscle with a mass. But in reality, just 20 years later, Young's double-slit experiment comes up, and it is shown that light is not a particle, it is a wave. And this whole concept gets thrown in the trash. So basically, nobody believed John Michell back then. But then 100 years passes. This was in 1783, so almost over 100 years passes. Nobody challenges Newton, even though there are these concepts which we cannot explain. Nobody challenges Newton because he's a big guy. So you see, in science also we have such prejudices which sometimes holds us back to really give a breakthrough new theory of things which we cannot explain. So in 1905, Einstein comes up with a revolutionary idea that the space which we live in might not be three-dimensional, not XYZ only, but there is a time dimension. So we are living in four-dimensional space-time. And what he says, he gives a series of revolutionary ideas for which people called him mad at that time. And he says that the happiest thought in my life was when I imagined a man falling from the roof. So obviously people would call him mad. You cannot be happy imagining a person falling from the roof. But what he meant was that he was trying to reconcile his special theory of relativity, which he had given in 1905, with the Newtonian mechanics and with Newtonian gravity. He was trying to understand whether gravity is a force or not. Now, if I tell you whether bodies fall towards Earth, right? So it is a force of attraction, it seems. But what Einstein is thinking is that, suppose, what is the acceleration due to gravity on Earth? It is 9.8 meter per second towards the Earth, right? The Earth is pulling. So he is thinking, what if I go in outer space in a rocket, I stand on a weighing machine, and this rocket, instead of accelerating downwards, it accelerates upwards with 9.8 meters per second square. What will be the weight of that person? If he is weighing 70 kilo on Earth, due to the same acceleration due to gravity, due to the same force supposedly, then what is the weight in space with the same acceleration but upwards? Turns out that the weight will be same. So Einstein says that what is the difference between this force of gravity and acceleration? I can always say that there is no force of gravity. It is just an acceleration which is causing a person to follow a particular trajectory, to follow a particular path when he falls from the sky. Einstein gives his famous equivalence principle in which he tells that there is no difference between gravity and acceleration. He tells that gravity is not a force. He tells that gravity is just a curvature of the four-dimensional world that we are living in. In that world, not only your distances vary if you are accelerating, but the time measured also varies. And that everything after because the speed of light has to be constant. Now we don't have to understand all these things. Our motive is to understand if gravity is not a force, then how do bodies move? Okay, before that, let us get a very simple exercise for you. For example, the sun and the earth. Newton says there is a gravitational force of attraction. Now, suppose the sun is to disappear. The sun disappears suddenly. Then, do you see the sun? Anyone? You still see the sun?
8 minutes.
There is an 8-minute of gap. Because of the large distance between the earth and the sun, and the speed of light is fixed, 3 to 10 to the power 8 kilometers per second, so it will take 8 minutes to reach you. So if the sun disappears, you will still keep on seeing the sun for 8 whole minutes. But if the sun disappears, what will happen to the Earth's motion? It is revolving in an orbit, and suppose you have a pencil, you have a string attached and a ball attached, and you are spinning this ball, and you suddenly cut the string. What happens to the ball? Exactly. And how much time does it take? Instantaneously, exactly. So you see this information, the same with the sun. If the sun disappears, the gravitational Newtonian force disappears, and the earth instantaneously flies off, according to Newton. But if we compare these two forces, the gravitational force and the electromagnetic force, due to which you are seeing the electromagnetic radiation, that is light, then the speed of light, doesn't it seem to be less than the speed of whatever is mediating this force of gravity? Say a graviton or whatever particle, which is bringing you this information that the sun has gone, the gravity is gone. This information is coming instantaneously to you, but the speed of light, due to being finite and constant, is taking some time. So this violates the concept that the speed of light is constant and it is the greatest speed any object in the universe can achieve. Then comes the discrepancy. So this Newtonian concept can anyway be discarded from your class 11th understanding, class 12th understanding. There is a discrepancy and you must think in this way. Because you should understand that whatever great discoveries have come up, they have come up with very simple thought experiments. The point is, you must come out of whatever you have read up till now and you need to think and imagine situations. That is what Einstein did. So, this force of gravity can not even be a force, because otherwise the particle that is mediating this force, similar to the particle which is mediating the force of electromagnetism, that is light, these two particles, the gravity, the gravitational particle will exceed the speed of light in free space. So Einstein said that, okay, now that we have discarded the concept of gravity, then how does particle move? Now, up till now, we know that this every elliptical orbit, all these orbits, we find the equation of the orbit from where? From the centrifugal and centripetal, all those accelerations we considered, and that the source of that is the gravitational attraction force. Now, the forces go on how to calculate how the particle's trajectory will look like. So Einstein says that there is no gravity. Whenever there is mass, say Earth, then the space-time in which that mass is sitting itself gets curved. More the mass, more the curvature. Now what happens? If you put a ball in a trampoline, a stretched trampoline, you put a ball. The trampoline will have a tip. Now if you roll another ball, it will follow a circular trajectory, not because there is a force. But this idea is a bit, this example is a bit contradictory because there are forces. But suppose that there is no gravity and this particle will have to take a curved trajectory just because the space-time in it, in which it is moving, is curved. For example, you walking on Earth and an ant walking on an apple, the ant will not see that he is walking on a curved line. He will go from point A to point B in a straight line. But you take the apple in your hand and looking, you will see that ant is actually taking this trajectory because the apple itself is curved. So the space-time is curved in which you are moving and in which every particle, including light, is moving. So you cannot walk in a straight line. There is no concept of straight line. There is a concept of geodesic or word line. And these word lines are dependent on the amount of curvature that is there in the space-time, and this amount of curvature, according to Einstein's equation, is directly related to the amount of mass that there is in the body. This equation is very complicated. Don't try to understand this, but the point is that the left-hand side of Einstein's equation, it says how much your space-time is curved, and the right side tells how much matter is there. So there is a famous quotation. Matter tells space-time how to curve. So suppose the Earth or the Sun, the amount of mass there is, the amount of curvature. Now the amount of curvature there is, if you bring in a second body, for example the Earth, depending on that curvature, it will have a curved path. The more the curvature, the more the curved path. So matter tells gravity, space-time how to curve, and the curved space-time tells the second body how to move. So it is, everything is just curvature of space-time. The distance that you will travel when you think you are traveling in a straight line, but you are not. So now that Einstein gave an equation, we need a solution for it, right? We have to know how the equations of motion come, what the curvature is around our celestial bodies like Earth, the Sun, and stars, and planets, and the whole galaxies, in fact, and the whole of the universe, in fact. What is the equation of motion of a particle which moves from point A to point B stated by these equations? For that, we have to find out the curvature of the space-time itself. So, the same way that Einstein gave his general relativity, Carl Schwarzschild comes up with a solution. So, he was equally as genius as Einstein. He solves equations, he comes up and tells that the space-time around any spherical star, which is not rotating. Stars are rotating, but he considered that spherical star which is not rotating. That star that this star can also form a black hole surrounded by the same event horizon that the center, which John Bishop finds almost 150 years back using simple classical physics. He comes up to the same event horizon and he shows that if this star, its radius is shrinked to within this event horizon, then it forms a black hole. Why? Because you can calculate the trajectory of photons in that space-time, in that surrounding, and you will see that the photons must fall into the central black hole. It cannot come out. So now, Herschel comes and gives this solution. There is a problem with it. That there is a singularity at the center. All the mass, 10 billion solar masses concentrated at one point. You can imagine physics breaking down there. Even today, we are trying to find out what the singularity is, and this is a drawback of Einstein's relativity. And here we can find a plausible explanation of what actually goes on at that small scale. You cannot say that Einstein's relativity is also 100% correct, which gives you an opportunity to find out what the real theory of relativity is, or the real description of gravity is. Please mind it, just as gravity is not a force, whatever Newton said was partially disproved by Einstein. Whatever Einstein said is also just a description of how our reality works, but not an absolute truth. We have not found out yet what gravity actually is, how do bodies interact, and whether we can explain the singularities which come up from Einstein's equation. So now, leaving this point aside, if you give a new theory, you will have to make predictions, right, which you can experimentally verify or disprove. So what Einstein's equation showed is that if you have a body which is curved in the space-time, and there is a star whose light is coming very near to this body, it will get reflected. Mind it will not get attracted because there is no force. It is just following a simple straight line path to the photon. It is following a straight line path from A to B. But since this surface is itself curved, it will follow a direction. But when you, over here, you observer, you are looking at this photon, you will know that light can bend. Your brain doesn't know that. It will never know that. You cannot reprogram it. It will always see the light coming from a straight line. So it will see the star's apparent location in a straight line, but the real location will be here. So you can test it. So what Edison did in 1919, he first took the photo of a star at night when there is no sun. And he noted the direction, the position, the coordinates, everything. Then he will have to again take the coordinates, note the position when the sun is there, because he's trying to see how the sun reflects, right? But if the sun is there in daylight, can you see a star? You cannot see a star. So what he did, he chose a total solar eclipse. What happens in a total solar eclipse that the sun is there, but you cannot see it because there is another celestial body between you and the sun. So the sun's light doesn't reach you, but every other point shows it is as if night, but with the sun. So it perfectly fit the experiment's requirements. He again measured the same star's position, and he saw that this time the star has shifted. That was a breakthrough moment. Everybody clapped. Einstein was right. He was no longer a madman. And the concept of gravitational lensing. See, what happens in a lens is that it bends right? So massive objects also bend right. So we call them gravitational lenses. They really are not lenses, but the phenomena is called lensing. So Einstein is proven right, and since 1990 to 2019, 2024, 25, we have been putting Einstein to every possible test possible. We have twisted his equations. We have tried to see from adapting from various directions, and every time he has come out to be correct. There was this LIGO experiment in 2015, which you might have read about. That is a collision of two black holes, astrophysical black holes, which gives out ripples in the space-time. Now imagine you have a perfectly still pond and you throw a pebble in it, then that will be ripples due to this collision. So what happens is space-time is also like a fluid surrounding your massive bodies. When two such highly massive bodies with highly curved space-time come and they collide with each other, then it sends out ripples of perturbation all throughout your space, and we could detect them actually in 2015, which was a massive test of Einstein's gravity, perfectly falling into what he expected, what he foretold. And also in 2016, we had this gravity experiment. These people were very smart. They were just looking at the center of our galaxy for 26 years. Now, the center of the Milky Way, like all galaxies, must hold a supermassive black hole with mass billions of solar masses. So, what happens there? The convection is very strong. So, stars also move in elliptical orbits. They don't move in straight lines. They revolve around the center of our galaxy. And these people, they observed for 26 years and they found out that they moved in the trajectories were exactly as predicted by Einstein. So all of these gave us very indirect proof of black holes, and also the center we could not see. There was nothing, there was blackness. There are the S2 stars, which we call them, a few hundreds of S2 stars, and they're just rotating around some unknown object which we cannot even see. There is darkness. So that's why these are all indirect tests. We have not seen a black hole yet. So what we try now is to find a direct proof. We try to see if we can find a black hole out in the universe. Before that, I'll briefly tell how black holes are formed. When stars are there on the sun, what is happening inside them is there is a huge temperature and there is huge fuel inside it, hydrogen mainly, and helium. What happens is there is a fusion going on due to this very high temperature. The hydrogen turns into helium. When all the hydrogen when all the hydrogen is used up, this helium then combine and we get higher and higher elements, even carbon and iron. So this takes up energy from the star's core. And what happens when the star is warm? There is thermal pressure outside. It's trying to expand. But remember, this is a huge amount of gaseous material, which is having a very high gravitational pull towards the center, and these two forces are actually balancing out each other. So the sun is there, it is not decreasing or increasing in size as of now, and in human scales it will not much. But what happens if this fuel is utilized? What is there to what is this red force which is pushing it outwards, this thermal pressure? It is gone. What happens if it is gone? What remains is the gravity. It will collapse all those mass, all those gases will collapse, the temperature cools down, and depending on the initial mass of the star, you will find a brown dwarf or a white dwarf or a neutron star or even a black hole. All those masses collided and collapsed into one single point. So that is how black holes are actually formed. And this limit of how high the mass has to be, the initial star's mass, so that again a black hole is given by Chandrasekhar in his famous Chandrasekhar limit. And you see that if the mass is very high, for example, greater than 8 times the mass of our sun, then we can have black hole or neutron star, and we have the black holes where the mass is actually bit over 10 solar masses. So that is how black holes are formed. Now, 2019, this is written in 2017 because the data was taken in 2017. In 2019 and 2021, we took the first real images of two black holes, one in a nearby galaxy, a 27 star, and one in the center of our own Milky Way galaxy, the Sagittarius star. And before explaining how we get the picture, I'm just giving you the idea of what the scales are. So the mass is 6.5 into 10 to the power 9 solar mass. The solar mass itself is 10 to the power 30 kilograms. So this is somewhere around 10 to the power 39 kilograms. This is 10 to the power 36 kilograms. The distances are 10 to the power 20 kilometers or 25,000 light years away from us. So we are looking at this object. We don't see it with our naked eye. We cannot see it. We are taking pictures of this now. This is as if standing in Kolkata, putting a grain of salt in Dubai and taking a picture with the camera. This is insane. We could not think how to do this. Also, this diameter is 50 microarc-second. Okay? So this 1 microarc-second is 10 to the power 10 to the power minus 9 of a degree. You divide a degree in 9 power, 10 to the power 9 powers, and one part is 50 microarc-second. So please don't confuse it with the size of the actual black hole. The actual black hole, the event horizon, this small black region itself is of the order of 10 to the power 10 kilometer in reality. But since it is 10 to the power 20 kilometers away from us, it is just a fraction of a degree of the sky, a point, a fraction of a point. So now I will explain how to image these black holes. But before that, I must tell you that what is this light? So as I explained, that to see something which does not give out a light, we have to place it in front of something which gives out a light. And we can make out how the shape is by the shadow or the path of the amount of the area of light that it blocks. So that is exactly the simple physics that is working on here. So this is how a black hole, a cartoon of a black hole. This is the accretion disk. Now the accretion disk is just a disk of very hot plasma and gases and electrons going around the black hole. But when we look at the black hole, it appears to be of this shape and also folded down. So what happens? This photon from the back of the disk is making a loop and coming to you. So the top part and the photon at the back of the disk is making a loop from below and reaching you, that is the downward part. And this way, over here, photons are making loops after loops after loops after loops. From 1 to 2 to 3 to infinite loops around the black hole. It's just going round and round. And for some perturbation, if it reaches you, it reaches on your screen as a distinct ring, which we call a photon ring, but actually it is a set of photon rings, which I will show you. It depends on the number of orbits it makes around the black hole before it reaches you. So this is actually what happens at the black hole's level, but when it is reaching you, you have to understand what happens at your screen to photograph it. So as I said, see, the photons are coming, they are having some wet orbits, and it could zero because it is not making any turns, it is coming, getting reflected and hitting your screen. And then, when you go to one orbit, see, it makes one orbit around the black hole. It comes and it hits you again on your screen. Then when you go to 2, it makes 2 loops and hits you. And all of these photons, when we put them together, of a black hole on your screen, as you will see. If you have a perfect telescope where you can find out every one of those orbits, you can make out all this light and dark streaks of light. But in reality, we do not have that. At least now we do not have the resolution capability of making a photograph as detailed as this, sitting from Kolkata and photographing a grain of salt in Dubai. We do not have that capability. But over here, you can see that this region over here is a dark region which we call the lens image of the event horizon. The event horizon is a bit smaller, but since the light bends and comes, and light appears to come in straight line. So your brain could see it a bit magnified. And then you have this region from where, as told you, the photon does not make a loop, but makes light turn and comes. This is the n equal to 0 photon region. And then you have n equal to 1, n equal to 2, and this, the innermost brightest ring is the n equal to infinity photon ring, and anything inside this would appear to be dim, and this is what we call the black hole shadow. Now, why is this important? We have taken a photograph, but why do you spend millions of dollars to take this photograph? It's because there is no way to understand what a black hole is, what is going around inside it. But this photon ring, it has all necessary information about this black hole, and this will be distinct as we go from one black hole to another. Now, please remember that Einstein's equation dictate black holes to be distinguished from one another only through its mass, its spin, and its electric charge. So if I have two bodies which have the same mass, spin, and electric charge, then they are the same. There is no other way of distinguishing the two black holes, and this is called the no-wave theorem of general relativity. So this shape and the size of this photon ring and the shadow region inside, it will be affected whenever there is a new physics inside it. Say dark matter or dark energy. If there is that is there surrounding the black hole, this photon ring's characteristics would change, and we will be able to detect if something else, some new physics is going on at such high curvature level. But also, we will try to know what is going on inside the black hole at the singularity vector. This is a problematic region. We are trying to come up with new theories of gravity, for example, quantum gravity, and we will be able to see whether our theory fits these experimental evidence to see how much our theory is deviating from GR, and if our theory fits the observations better than GR. So that is why black holes are very important, because we are getting a laboratory to test gravity directly. So I have already explained what these regions are. So I will skip this. Now, how do we photograph a black hole? You cannot just take your cameras or your phones and just click, see, you will see nothing. So we need telescopes for that. But what kind of telescopes? Now, the radiation that is coming from a black hole, so black hole is there and the radiation is coming, it is not free space. There are galaxies within it, there are stars, there are other solar systems. The light is coming from there and reaching you. What guarantees that the light will reach you in the first place? That it will not be scattered away by the intervening material. So it turns out that light does get scattered away. Most of the visible light gets scattered away, so you cannot see a black hole with your naked eye, because we see only visible spectrum of the light. Even the high energy region, gamma rays, X-rays you cannot see. What does reach us are the longer wavelengths. For example, radio wavelengths. So we have some black holes in radio at 1.3 nm. Now you might have read that this Huygens principle, interferometry. Whenever we want to distinguish between two objects, firstly, how do we measure? How do we see one object? So the wave theory of light tells you that whenever the light comes and reaches you through a thin slit, or two thin slits, or more than two thin slits, it is never a point on your screen, but rather a series of light and dark fringes, which we call the interference pattern. That is how wave optics actually works. So, what we have to see is that this interference pattern, if there are two objects that you are trying to differentiate from one another, they are not overlapping or separated, then you have to make sure that the two light rays that are coming and hitting your screen and making this interference pattern, it follows the Huygens principle, and the maximum, the bright fringe, the central maximum of one of the objects, light rays, must overlap at least with the first minimum of the other. So, if you have not read wave optics, so you don't have to worry about it. But the criteria is that my telescope will see two objects separately and not one overlapping or blurred. Is that the resolution of this telescope is given by the wavelength in which we are measuring and the aperture of the diameter of the telescope. So this is basically the equation in which we put in our requirements. We put in this 1.3 mm, we put in the required angular resolution. Remember I told you that the photo of the black hole, it has an angular size of 50 microsecond. So we are trying, we have to be able to distinguish 2 points of that image at least to 10 or 20 microsecond, so that each point on the image does not get overlap on top of each other, and they are separated, and you see the fine structure. And if you put in those numbers, we see that the diameter of the telescope which is required is 13,000 kilometers, which is the diameter of the Earth. So if you don't have that big a telescope, you can never be able to photograph the black holes that you are photographing in principle. So what is the way out? We do a very clever issue. Suppose this is the basic setup of a telescope. So a wave front comes parallelly and falls, and it falls in a secondary mirror or lens, and it gets reflected, and they meet, and you find an interference pattern. The maximum of that interference pattern will be your image. If say this light is coming from a point source, for example, a star. So at the present, let us consider it is not an extended source, but it is a point source, a star. We are trying to focus on a star. So can we break up this mirror such that some of the rays still follow this trajectory and reach us? I think we can do that. We will lose some of the rays from in between, but we will still have the overall requirement that they reach me in following the same path length. So if we remove these unwanted pieces, what we can do is we can replace a big mirror with smaller mirrors but following the same path. So what we do that exactly. Instead of mirrors, we put telescopes in these two places. We remove the rest of the telescopes and we try to see if the lights coming from those two can be correlated and they can be formed into a mirror, into an image of the same mirror, the same big mirror that we were expecting. And so that is how you can now make a telescope of a diameter much larger than this diameter, which was much smaller. So this is basically, there is a lot of complicated physics behind this. This is a rough idea how we managed to do this. So this is a bit of math. If you have not read interferometry, just a simple explanation will be, if there are two telescopes which are separated now by the baseline B, instead of the diameter of your telescope, we have now two telescopes separated by D, which is now your effective diameter. And then from the same star, two rays come and hit your telescope. Due to the separation of the telescope from very normal trigonometry, you will see there is a path difference between these two waves which are hitting your telescope. And due to this path difference, there will be a phase difference. And wherever there is a phase difference, there is a distinct interference pattern which you get on your screen. So this interference pattern is what we want, and we keep on changing this telescope distances and the number of telescopes. We correlate them together and find the final signal, and from there we try to reconstruct the real image using inverse Fourier transform. So this is a bit mathematical, but the thing is that the electric fields are coming, they are interfering. You get time average the electric fields, and what you find is that this time average of the two electric fields is actually a Fourier transform of the intensity in the source. And now if you want to find the intensity at the source, as you will see on your screen, you just have to do an inverse Fourier transform. This is the thing which we measure from the telescope, and this is the thing which we do a math to get. We do not, that's why these are not direct images, they are direct observations of the intensities, but they are reconstructed images of those intensities. From here on it will be a bit technical, but I think I should let you know, because afterwards some days you take this up, these will be there in your mind. So we did 8 telescopes and also some telescope arrays. I mean, many 27 telescopes are there in a big location. So we correlate all of them. We let, suppose that is a black hole and the light is coming and falling 2 different telescopes on 2 different locations on Earth. We correlate the two, and then we take another telescope and we let the light again fall. We take again the measurements of the electric fields, and we keep on doing that with each other, all the telescopes. We correlate them together, we join them together at 2 central facilities. One is the Maxwell Institute in Germany, and one is the MIT Observatory in MIT, USA. And we reconstruct the final image, and please note that this is 350 TB of data taken over 4 days. As the Earth rotates, your telescope's angles will also be rotating, and you will keep on picking up different baselines. Over here, the important part is to fill up this UV plane. This UV is just coming from your wavelength, and this UV plane has to fill up to actually get the whole of the image. So now that we connect all the telescopes, we have an effective baseline of 13,000 kilometers, which is effectively the diameter of the Earth, and the angular resolution is 10 microarc which we needed, which is this amount of a degree. I mean, you divide this by how many zeros? I mean 9 zeros maybe, and then you get the image of a black hole. So this is a video. Hope this will. So we need an Earth-sized telescope, which we cannot have. So what we do instead, we put many different telescopes all over the Earth, and we take 2 telescopes at a time, a pair of telescopes, to do our math of Fourier transforms. We join them as the Earth rotates. New telescopes come into view. 2 telescopes at a time, the Earth rotates, and you picture a part of your sky. Then for different orientations, you put the data together, you reconstruct a part of your image. You put the telescopes closer by. As you put them closer and closer, you have blurrier images going upwards. And our aim is to fill up the Earth with as many telescopes as possible to have the complete data, but telescopes are costly. And at present we have 10 telescopes. We will try to expand it to 15 telescopes, and we will have better and better resolution. So as the Earth rotates, these telescopes take images from different angles. And this is a UV plane that I was speaking about. We need to fill up this UV plane with all points of data, but at present it is anyway very sparse, it is not very complete, and we especially have two very large data gaps. So we have to construct the image of a black hole from this few data points. It is like playing a piano with keys missing, and you just guess how the song can be because you have some idea about the song. Until you have a new piano, you have complete finer and finer pianos with all the keys, missing keys coming up, and you fill up the data gaps, and you keep on improving your image. So at present we use supercomputers to collect all those vast data sets from the black holes, and we complete them with rapid simulations as well as complex data analysis. And there are various techniques which are using machine learning also to enhance this sparse data. Sparse means very few data, separated data, not very dense data. And we uncover what patterns are there. I mean, at present we can only tell that there is a ring and there is a darkness. That is what we can tell at present. But in the future, we would like to actually have better resolution images. And there are many algorithms to not only fill in this data gaps, but also subtract the noise. Now, this is very important. The radio telescopes are on Earth. We are using mobile phones, we are using internet, we are using every electronic device which radiates in radio waves. So those are your noise. The telescope does not know that which is my good signal and which is my noise. It picks up all the signal that falls on it. You have to separate this noise from this the data, and those require algorithms like clean, with which we clean the noise away, and RML. I will explain what RML is. So the clean algorithm is like, this is a very noisy. This is my
Some.
The power is it is big.
Better in here.
Switch
Switch on.
Hello.
Yeah. So over here we have this is the data which we have in our UV plane from all the telescopes put together. So over here, this is actually my signal, and these are all the noise. Can you see the noises are so big? But the signal is always the brightest. So what we do, we separate first the bright spots, the brightest spots, and we replace them with smooth functions. What we try to do is iteratively smooth out the noise, and we are left with only our signal, and the noise is subtracted and integrated out. So what we do once we have this clean data, now we have to reconstruct our image from this data. This data is simply your voltages across your telescopes with a timestamp at which time the voltage was recording. That is your data. But this is a very different image that we are trying to reconstruct. So what we do, we try to take Einstein's gravity, gravitational theory, and we try to change various parameters in the theory: the black hole mass, the distance, the spin, the accretion disk temperature, the accretion disk model, the distance of the black hole from the Earth. We try to vary everything in very small steps, and we try to come up with a whole library of images, what we expect to see, and the data which we have, we try to go backward and try to see which of the images this data fits the best. For that, we use probability, we use Bayesian statistics to select the most probable image from this radio astronomy RNN library, which we construct first. And we put in some prior knowledge, for example, the expected ring structure, which we expect to see from gyro negativity, to favor the most realistic images, and we pick up, say, the top 5 or the top 4, and then we average these 4 best fit images, and we find the final image. So these are the number of library images that we create. Then we discard all those images which do not fit realistically our expectations. We are left with top 4 or 5 images, and then we average out and arrive at the one best fit image. So this is the whole process. We let the Earth rotate. We take the data, we store them in hard drives. 5 petabytes is 5,000 terabyte, and 1 terabyte is 1,000 gigabyte. So you can imagine how much data is there. You cannot transfer it over internet. You have to physically take your hard drives from South Pole, from America, from Hawaii, and from everywhere. 2 locations. One is in Germany, one in USA. You have to correlate the data. You have to do the fringe fitting and the image reconstruction using the 2 algorithms that I told you, and also many other algorithms that go behind it. And we finally do the announcement in 2019. This whole process takes 2 years. And this is M87 for Sagittarius at the center of our galaxy. This imaging that was even more complicated. It took 4 years because it is smaller in mass and it rotates very rapidly. So in the 4-year time span that I am observing, the black hole has already made complete rotations, and its structure has changed. So for that, it took a bit more to image Sagittarius at the center of our galaxy. But we did that, both of them. And what we did is a final image of the black hole. Now, the question is, why do we do all those things? Why waste all that resource, money, to gain what? So as I had said, that the shape and size of the black hole shadow is only dependent, mind you, on the background space-time geometry, which is dependent only on the background theory of gravity. So if we measure them correctly, we know what theory is actually correct, whether Einstein's theory is correct or whether it is not, and whether if we give a new theory, whether it fits the observations more accurately than Einstein, and we have some other physical descriptions of gravity which we do not have for surety at present. Also, we do not have access, direct access to the singularity of the black hole, because light cannot escape from there, so no information reaches us. So we know that physics must break down because so much mass cannot reside at one point. That is not sense. Common sense. So what actually happens there? We can only indirectly have some idea from the gyro. We need more tests for that, and also we can fulfill our long dream. It was also the dream of Einstein to unify quantum physics and gravity and find out how gravity works at the center of the black hole, at the Planck scale and energy, which is very high energy and a very low scale. And ultimately, we want to find a way to arrive at quantum theory of gravity. So the future of black hole imaging is even more difficult and of high aspirations. We want to come up with next generation event horizon telescope and even use telescopes in space to combine and get an even larger network of telescope with a effective baseline of even greater than the Earth, a bigger telescope than Earth itself. And we want to then not only photograph black hole but also videograph a black hole. So you can imagine how big that ambition is. And for that we might have to wait for another 15-20 years or even greater than that. But when we do, and we are very positive that we will be imaging the center of the black hole in real time. The time is ticking over here, you can see. And for that, we will have to image the black hole not only at 1.3 and 0.8 mm, but at higher frequencies also. For that, we need more sensitive telescopes. And since we are using multi-wavelengths, 1.3, 0.8, and even smaller wavelengths, so that will be a multi-wavelength observation of the black hole. And also, day by day, we are advancing our imaging techniques, the machine learning algorithms, and noise clearing algorithms. And we are aiming to capture high resolution black hole images and movies. So it is up to you how you want to join in this effort, and whether you can or you will stumble upon some new physics, just like Einstein did. And there are scopes and there are necessities actually to take up this field because we do not know the real description of gravity, and you would see, you would feel that what is the need of all those things? What if Einstein never came up with this gravitational theory? How would we be affected? We were happy with Newtonian physics, but remember, if Einstein did not come up with his gravitational theory, then all your GPS will not work, your Google Maps will not work, your satellite will not work, because in the International Space Station, time ticks slower than your clocks because it is away from an accelerated frame. Earth is an accelerated frame, it is away from an accelerated frame. So we need Einstein's equation to find out the dilated time over there, match it with the time over here, to give you real live location which you get on your Uber apps, your delivery apps, your Google Maps, everything. So that is why you should always take a fundamental physics, because the implications are huge and they change our technologies. With that, I thank you and I will take questions and answers.
Thank you, Mr. for this wonderful talk. Apart from the mathematics, আমরা আজকে দেখলাম black hole, most mysterious scientific thing in this century. How massive it is. And main problem is we can imagine properly. So Misba has explained the way out how we can imagine black hole in our lab or in our different setup. So thank you again. If you have any question, anyone?
Good afternoon, ma'am. In our reality, every entity have its opposite. Even in molecular space, there is attraction and repulsion. So my question is it possible to have anti-gravity just like gravity exists?
Yes, the answer is yes. If you say if it is possible, everything is possible. Because we have not arrived at a complete, absolute theory of anything. We do not know anything and we cannot rule out anything at present. What we know about the universe is a fraction of what the reality is. So if you say that whether anti-gravity can be present, of course it can be present, If you tell me whether it has been observed up till now, there have been experiments, but we do not have any conclusive results saying that yes, it is present. But intuitively, we can say that exactly the photos which I told you, those do show these anti-gravity effects. And gravity itself is very anti to what we thought about it up till now, and up till Einstein created its theory. So this concept of force being there is already nullified to some extent, and I'm sure we can always stumble upon anti-gravitation.
Any other question?
Ma'am, can you tell me anything about Hawking radiation?
Okay, Hawking radiation. Simply speaking, as I said that nothing can escape black holes, but Hawking showed that some things can in a different way. For example, when you have a particle and antiparticle moving very close to the black hole's event horizon, one of the particle, if it falls down, the other will have to go out. So this is how the Hawking radiation from that particle which escapes, we call that the Hawking radiation, and that is directly related to the area of your event horizon actually. So that is what Hawking radiation is. At your level, sir, I'm just saying.
Any question? If not, then I want to ask. So, hello. So, last that you said about Bayesian, Bayesian statistics, right? So you use to reconstruct this image. So here you are taking Einstein's theory as prior. So it's kind of biased. Do you not think it's kind of biasing your measurement?
Yes, yes. So that is what we did for M87. For Sagittarius, what we did, we took a lot of theories of gravity actually. And we found that Einstein's theory was the winner. So we took all, this Einstein, dilaton, gravity, and all the other, some of the other theories that was with Carl Newman. Even Carl Newman was not fitting very well. So it was just Einstein's theory fit the best.
And another question is that your measurement time is quite large, right? How long?
4 days.
4 days.
So Earth makes complete.
That's small with respect to the time scale of the event.
Exactly. But even for Sagittarius, which has the order of days for one rotation, the 4 days which we took, it was a fraction, sizable fraction of Sagittarius's rotation. So it rotated quite a bit. That is why reconstructing it was a bit difficult. It was 4 days, and say that is some, I don't remember, some 20 days maybe. That is 1/5 of the fraction already.
Thank you.
Misba, on slide there is a horizon radius. That was written, we go over 2 by 6 square. So I think it will be 2 by 6 square. Third or fourth. First one.
Sir?
The event horizon radius.
Yes.
Is it 2 by 6 square?
Yeah, I think it will be 2 by 6 square.
It is not wrote over there.
Sorry. Yeah.
It is
Yeah.
only 2 by 6 square. Okay.
2 by 6 square. Yes. Sorry, I copy pasted it.
Okay.
So then it's not matching with the
Newton said it will not be matching. I think I skipped that part. Newtonian theory also gave an estimation for this curvature, which was smaller than this given by the Einstein's this thing. So that is why this will not be matching. It did not match when I invented, and it matched Einstein's instead of Newton's. So sorry for the.
Thank you again. আমার মধ্যে উপস্থিত আছেন আমাদের আইপিএসসি কোঅর্ডিনেটর ডক্টর পার্থ পাত্র। আমি ডক্টর পাত্রকে স্টেজে আসার জন্য অনুরোধ করছি। Few words from me.
আমার আন্তরিক অভিনন্দন শুভেচ্ছা আইপিসির পক্ষ থেকে আন্তরিক শুভেচ্ছা জানাই ম্যাডামকে ইনভাইটেড স্পিকার হিসেবে এসেছেন আমাদের একটা সুন্দর বিষয় নিয়ে আমার সামনে তুলে ধরেছেন। আমি আশা করি আমার ছাত্রছাত্রীদের অনেক উপকৃত হয়েছে এবং আমরা অনেক কিছু শিখলাম জানলাম। ম্যাডামকে খুব ধন্যবাদ জানাই। আর আমাদের এই অনুষ্ঠানটার যে সঠিকভাবে সবাই মিলে করেছে যে যারা অর্গানাইজ করেছে তাদেরকে ধন্যবাদ জানাই আইপিসির পক্ষ থেকে। এবং এরকম অনুষ্ঠান যেন আমাদের মায়ের সাথে হয় আমাদের ছাত্ররা খুব উপকৃত হবে এই বলে আমি আমার বক্তব্য শেষ করছি।
আমি ডক্টর পাত্রকে অনুরোধ করছি ডক্টর মিসবার হাতে মেমোটা তুলে দেওয়ার জন্য।
Stage.
আমাদের সেমিনারে এসে উপস্থিত হয়েছেন আমাদের এক্স টিচার ইনচার্জ ডক্টর নাসিরউদ্দিন মন্ডল। নাসিরউদ্দিন মন্ডলকে আমি স্টেজে আসার জন্য অনুরোধ করছি।
হ্যালো, ফিজিক্স ডিপার্টমেন্ট আমাদের কলেজের একটা সমৃদ্ধশালী ডিপার্টমেন্ট। এরা যে আজকে ব্ল্যাক হোলের উপরে একটা সুন্দর সেমিনারের আয়োজন করেছে, ওয়ান ডে স্টেট লেভেল সেমিনার, যেটার জন্য আমাদের স্টুডেন্টস এবং স্টাফরা অনেকেই যারা আগ্রহী অনেক উপকৃত হয়েছেন। এবং যিনি আজকে এই সেমিনারে উপস্থিত হয়েছেন মূল বক্তা হিসাবে মিসবা ম্যাডাম। মিসবা, আমি ওনার সম্পর্কে শুনেছি, ওনার মামার কাছ থেকে। আমি একই সঙ্গে আসি, আমার বহরমপুরে উনি থাকেন। উনি বলেছেন আপনার সম্পর্কে আপনি কান্দির এই সোয়াইলেরই একজন সন্তান এবং আপনার মা আমাদের ডিপার্টমেন্ট মানে ফিলোসফি ডিপার্টমেন্টের হেড, আমাদের ডিপার্টমেন্টেই পড়াশোনা করতেন। তার জন্য ওনাকে একটা অভিনন্দন জানানো উচিত। স্টুডেন্টরা আমাদের কলেজের তরফ থেকে ওনার মাকে স্পেশালি একটা কনগ্রাচুলেশনস জানান। এবং মামা সব আমাদের কলেজেরই স্টুডেন্ট ছিলেন এবং সেটা সব থেকে বড় কথা, আমাদের বলয়দা তার মায়ের কলিগ মানে স্টুডেন্ট বন্ধু ছিলেন, ক্লাসমেটস। এটাও বলয়দার সহযোগেই মনে হয় মিসবার খবর আমরা পেয়েছি, ফিজিক্স ডিপার্টমেন্ট পেয়েছে। উনি যে ব্ল্যাক হোলসের মধ্যে এত কঠিন একটা দুর্বোধ্য ব্যাপারকে সুন্দর করে তার ডায়াগ্রাম ইমেজের সাহায্যে ভিডিওগ্রাফির সাহায্যে তুলে ধরতে পেরেছেন। এটা ইনি অনেক দূর যাবেন। ওনার প্রতিভা দেখে খুব ছোট, আমাদের থেকে অনেকটাই ছোট। আমাদের ফিজিক্স ডিপার্টমেন্টে যারা পড়াচ্ছেন সব থেকে জুনিয়র, তার থেকেও মনে হয় ছোট। তো এত কম বয়সী নিজে একটা প্রশ্ন করছেন এই দুর্বোধ্য বিষয়ের উপরে, তার জন্য আমরা আমাদের কান্দিবাসী হিসাবে আমাদের কলেজের দিক থেকেও আমরা খুব গর্বিত অনুভব করছি। অনেক ধন্যবাদ আপনাকে। ফিজিক্স ডিপার্টমেন্টের হেড তাদের এবং ফিজিক্স ডিপার্টমেন্ট ও অন্যান্য টিচারদেরকেও আমি ধন্যবাদ জানাচ্ছি এইরকম একটা সুন্দর অনুষ্ঠান আমাদের কলেজে অনুষ্ঠিত করার জন্য। থ্যাংক ইউ। এবং এই বলে শেষ করতে চাইছি, আবার মাঝে মাঝে যেন আমাদের কলেজে এরকম সুন্দর অনুষ্ঠানের আয়োজন করে এবং আপনার মতো সুন্দর সুন্দর বক্তাদের, গণ্য বক্তাদের আমরা তাদের অনুষ্ঠান শুনতে পাই। ধন্যবাদ।
অনুরোধ করবো মিসবা আপনাকে একটু ছোট্ট গিফট তুলে দেওয়ার জন্য। আমাদের প্রিন্সিপাল ম্যাডাম খুবই কাজে ব্যস্ত ছিলেন, উনি চলে এসেছেন। আমি ম্যাডামকে অনুরোধ করবো স্টেজে আসার জন্য এবং মিসবাকে সার্টিফিকেট তুলে দেওয়ার জন্য। সূত্রে আজকের এই সেমিনারে আমাদের ডক্টর মিসবাকে পাওয়া বলা ছিল যে আমি অনুরোধ করছি একটু স্টেজে আসার জন্য, মিসবাকে একটু গিফট তুলে দেওয়ার জন্য। Thank you, Dr. Misba. To be present here in this one-day state level seminar organized by Department of Physics. Also, I want to give thanks to our family members who are present throughout the seminar. I want to thank our principal madam, Dr. Samadata Masha, our IQC coordinator, all our departmental colleagues and other colleagues from college, our non-teaching staffs. Last but not least, our students. Okay, thank you all. আমরা আমাদের সেমিনারটা এখানে শেষ করছি। ভালো থাকবেন এবং দেখা হবে সকলের সাথে। কি ঘোষণা, আমাদের একটু ছোট্ট আইটি অ্যারেঞ্জমেন্ট আছে বাইরে, সকলে একটু আসবেন।